Now we've already discussed the graphical methods. Okay. Now we'll be talking of the algebraic solutions. Okay. Now, when we talk of algebraic solutions, that means we are assuming that we have at least three variables. Otherwise, we could have solved them graphically. Okay. So let us assume that we have n number of decision variables with us. Okay. So that means now I'll write my objective function. Now, objective function was a linear combination of these variables. So I'm taking them as CJs, okay? C1, X1, C2, X2, and so on and so forth, Cn, Xn, okay? And this objective function Z that we have defined, this is going to be either maximized or minimized, right? Now, subject to, we have constraints, right? So let us assume that we have m number of constraints with us. Okay. So we have n variables and m constraints, right? So that means if I say m constraints, that means my inequalities, the first, basically m constraints means I have m resources of which we are discussing things, right? So the first resource will define the first constraint, second resource, and so on and so forth. We have m constraints with us. Now, to write down the constraints, of course, they have to be again linear combination, linear inequalities, right? So let us take the coefficients as a11. So a11 would mean, I'll just write down the equation first and then I'll explain. A1 and Xn. Now this will be either less than or equal to or more than or equal to or equal to B1, right? So A11 is the per unit utilization of the first constraint for the first decision variable, right? Similarly, A12 becomes the per unit consumption of the first resource for the second variable, and so on and so forth, right? Similarly, the second constraint would be something like this, A22x2 plus A2n xn, and of course, less than or equal to B2, and so on and so forth. Since I have m constraints, so I will have m number of inequations, okay? And this will be either less than or equal to so on and so forth, bm, okay? Now, of course, apart from this, we have the non-negativity restrictions that all my x1, x2, xn's are going to be more than or equal to 0, okay? So basically, what we have done is, if I denote the X, capital X, as the matrix x1, x2, xn, because I have n number of constraints, I define the matrix B as B1, B2, Bm. Okay. I define the matrix C as C1, C2, Cn, and I define the matrix A as A11, A12, A1n, and so on, AM1, AM2, AMN. Okay, so this matrix is going to be M cross N. Okay, M rows and N columns. Okay, this is N cross 1, right? This is M cross 1, and this is 1 cross N. I've written like this, okay? But then, because I want to write the problem is going to be maximize or minimize, which I can write as Cx. Of course, I can rewrite C's and X provided this product Cx exists, okay? Subject to Ax, okay? Now, I have three options. It can be less than, more than, or equal to B, and the non-negativity restrictions. Is that okay? So this is how a typical linear programming problem will look like. Of course, we can, I mean, this, of course, I'm assuming that this product exists, and this equality exists, and so on and so forth. So that matrix requirements are being satisfied here. Okay. Now, if you just, now we are developing an algebraic method of, solving this problem. Now, as I said the other day, your basis for developing the algebraic method is going to be your graphical method. Okay. In the graphical method, what did we do? We obtain what we call as the feasible region. Okay. Now, because it was a graph, we could see the region, right? And what was the speciality of this region? The speciality of this region was that all the points that lie in this region, they satisfy the constraints simultaneously, all the constraints simultaneously. This was the advantage of the feasible region, right? So now, since I'm not drawing it, I'm not plotting it, so instead of calling the region, I can call them as the feasible solutions. Okay, so feasible solutions would mean all those values of x1, x2, xn that satisfy all the constraints simultaneously. Okay, this is the first thing that we identified. The second thing that we identified were the extreme points. यही किया था of the feasible region. And I said these points are actually your basic solutions. Okay, why we call them basic? Now you will understand the reason why we are calling them as basic. Okay, so this is going to be my next step, that identify the extreme points. So see, why I'm doing all this is because this graphical is something that you have already seen what is happening, right? What is going to be the corresponding term in the algebraic method of solving? Now I'm going to just explain that. Okay, so like for feasible region, you have feasible solutions, right? Similarly, for extreme points, we'll be talking of basic solutions. Now, what did we do once we had identified the extreme points? It was like we listed them, okay? And we obtained the value of z at each of the extreme points, right? So when you are computing the value of the objective function at each of the extreme point and then judging whether this should be the solution or not. So basically what you are trying to do is you are trying to find the solution, of course, solution at a particular stage, right? See, now listen to this carefully. When I say, see, supposing you had one point O, what were the coordinates? 0, 0. This was an extreme point, right? You evaluated Z, right? The Z turns out to be 0 for this. Now, this is what? The value of the objective function. Where? At this extreme point. So basically, what is this? This is your solution, or this is your one of the basic solution for which you have obtained the optimal value at particular instant, not total. Okay, so at this particular stage, this is the value of the objective function, right? What do you do then? You look at another point A, you have the coordinates for this, you compute Z, right? Supposing this turns out to be 10. I'm just assuming, okay, and these points are say 1, 2, any A, right? Now what has happened? The value, see, your problem was say maximization type, right? So what has happened? Your value of Z has improved from 0 to 10. बढ़ गई ना? The value of Z has increased. As you have done what? You have moved from one extreme point to another point. So basically, what have you done? You have moved from one basic feasible solution to another basic feasible solution. And in this process, you observe that your value of Z has improved. We yet don't know whether this solution is optimal or not. Okay. Now, because the problems that we tried so far, we had fixed number of extreme points. So we listed all the extreme points first, we computed all the z's first, and then chose the maximum z, right? But say supposing you have too many extreme points, or like when we'll be doing in the algebraic, I don't want to compute extra. Why should I compute extra if I can devise a method which will tell me that If this happens, then the current solution is going to be an optimal solution. So if I'm able to devise such a method, so what will happen? It will serve two purposes. Number one, I will get to know whether the given solution is optimal or not. Number two, I need not compute the value of the objective function at the subsequent extreme points because I've reached my optimal. Okay, so the other is not required. So basically, what we are going to learn in algebraic method is number one, how do we identify the basic solutions? Where do we start with? अब यहाँ तो हमने randomly, मैंने O से शुरू करा, किसी और ने A से शुरू कर दिया, किसी और ने B से शुरू कर दिया, तो सबका procedure तो different हो गया. तो but see, what will happen is obviously because we are handling the same problem, the optimal solution will be same. But say supposing for a given problem, if point B is an optimal solution and somebody starts with B, तो उसका तो एक ही step में optimal आ गया. But say supposing I start with O, I might have to compute more number of steps to reach the optimal solution at B. Okay, so to remove this disparity, we have to have a uniform basis that no matter from where, maybe sitting at home at different countries, somewhere, no matter where we are solving the problem, all of us must start with the same basic solution. Okay. Once we start with the same basic solution, obviously the number of steps required to reach the optimal will also be same for all of us. Okay. So that means now for algebraic method, we have to learn what should be our starting solution. ठीक है ना, ये हमारी एक तरह से ये स्टार्टिंग सोल्यूशन होगी ना हमारी कि हम शुरू कहाँ से करें, ओ से करें, ए से करें, बी से करें, किससे भी, जिससे भी मर्जी करें, बट all of us should start from the same starting solution. Okay, so we have to identify this. What is our starting solution? Number one. Number two, we must identify when to stop because I don't want to compute extra. मुझे क्या जरूरत है कि I compute, supposing my problem has say 50 constraints and say supposing I have say 100 variables and I am solving it. So imagine the number of extreme points we are going to get, number of basic solutions we are going to get. So why should I compute for all such numbers? Maybe if I devise my method so in such a manner that I am able to reach the optimal solution at the earliest. Okay, it will suffice. I need not compute for the remaining extreme points. Okay, so this is what we have to learn. How to move, how to improve the value of Z. Okay, so supposing you had a situation where your feasible region is something like this. Okay, so you have O, A, B, C, D. Okay, now I start from O. Supposing B is optimal. Supposing my objective function is such that B will give me an optimal solution. Now I can move from O to A and then B. Right, so how many? 1, 2, and then I've reached my optimal. But say supposing somebody else starts from O to D to C and then B. So this path is going to involve more calculations compared to this path. Okay, but then you are moving. So basically, if I devise a method which tells me that if instead of moving from O to D, if I move from O to A, I will reach my optimal solution quickly. Obviously, I will move from here. Okay, so this is what the algebraic method is going to tell us. What is going to be the next best optimal so that you reach your optimal at the earliest. And once you have reached optimal, somewhere, somehow, we must know when to stop computing. Say if I'm moving from O to A to B, I reach here, I need not compute for C and D because I know this is going to be my optimal solution. Okay, so I must know when to stop. I need not compute it further. So this method or this technique that we are going to develop is actually an algorithm. So algorithm means what? It should be a step-by-step instructions that need to be followed. Okay, how do you have to start? how do you have to move. So if this happens, then you have to do this. If this happens, then you have to conclude this. And if this happens, then you have to stop. So all those conditions, which are going to govern, that will be covered in this algorithm. And this algorithm is called as the simplex algorithm. Okay. So simplex algorithm is basically a method, an algorithm to solve the linear programming problems. And so far till date, it is the best. There is no other method which can improve the solution procedure of a given linear programming problem. Is this clear? Hmm? Is this clear to all? Okay. Now, before we begin with the algorithm, we have to learn a few more concepts. See, okay, let us consider. I'm just taking an example from your book. It says maximize 25x. Of course, there are only two variables because they want to show the parity between graphical and algebraic. But I'll just explain. Subject to 20x1 plus 30x2 less than or equal to 690 and 5x1 plus 4x2 less than or equal to 120 and x1 x2 more than or equal to 0. Okay, now of course if we were to solve it graphically, things would have been much more simpler because you just plot two straight lines, you identify the feasible region, you have the extreme points, and you can solve it. Okay, but now I'm trying to solve this algebraically. Okay, now graphically still it was easier to handle the inequalities, but graphically or algebraically we cannot. We have to convert the inequations into equations at any cost, otherwise we cannot handle it. Okay, uh, this is inequality. I cannot just straight away remove this less than or equal to sign and I say let it be equal. ऐसा तो नहीं कर सकते because they are physical quantities. Random तो नहीं है कुछ भी, ठीक है? Like in this case it was wood, lumber, ठीक है? So this is the constraint related to lumber, right? And this is the constraint related to labor, the manpower. Okay, so I cannot just remove the inequality and replace that with equality. Okay, so what we can do here is, now see, if I say if I have a less than or equal to sign here, that means what? That means basically your left hand side is somewhat less than or equal to your right hand side. ठीक है ना? This is the thing. Now to convert this inequation into equation, what should be done? We must add something on the left hand side, something, some variable. Okay, so that means what are we doing is we are introducing a new set of variables. Okay, say x3. This is again a variable. See, already my x1 and x2 are variables, but then these x1 and x2 are my decision variables. Okay, in the sense that they correspond to something that already exists physically. Okay, say मान लो, say x1 was the number of tables that should be produced and x2 was the number of chairs that should be produced by that carpenter. Okay, so they belong to some physical quantity. Okay, that's why we are calling them as decision variables. But now what am I doing is I'm incorporating another variable x3. Okay, but this x3 is being incorporated in the constraint. Of course, it will have to be incorporated in the objective function also, but with some restrictions, in the sense that if I'm incorporating this x3 in my constraint, see, basically, what does this less than or equal to type means? This means, see, my left hand side was the utilization of the wood and my right hand side was the availability of the wood. Okay, that means if I interpret it like this, when I say that this has to be less than or equal to, that means my utilization can be at the most equal to the availability. ठीक है ना, ये तो बिल्कुल ही परफेक्ट सिचुएशन हो गई ना, कि जितना अवेलेबल था मैंने सारे का सारा खत्म कर दिया उसको. But that is too ideal a situation to exist in nature. Okay, so that's why most of the times it is less, in the sense that whatever you are using is actually less than what is available to us, because you have to have something left with you for the next day or something like that, right? So basically what is being happening here is that there is some slackness in this resource, in the sense that it is not being utilized completely, right? So what we can do is we introduce a variable x3, we call it as the slack variable, and what it does, it converts the inequality into equality. That means my first constraint can now be written as 2x1 plus 30x2 plus x3 equal to 690. Now, if in the subsequent process of solution x3 turns out to be 0, so that means there was no slackness in this. Okay, but because I'm assuming that there could be some slackness, so that means I have a chance that this variable could be non-zero. So I introduce that. So whatever is the difference, or whatever was the slackness, that corresponds to x3, and my inequality can get changed to equality. Okay, similarly your second constraint also by chance was less than or equal to constraint, so for that constraint I'll introduce another slack variable x4 equal to 120. So that means your slack variables, in this case the number of slack variables that we have added is actually equal to the number of constraints, provided all your constraints were less than or equal to types, right? Now since we have added them in the constraint, so they must be present in the objective function also, right? But of course, we also assume that because my decision variables were non-negative, so we can always assume that slack variables are also non-negative. Okay. Now, in your objective function was actually 25x1 plus 30x2. Okay. So it could be like 25 is the per unit profit earned from one table. 30 is the per unit profit earned from a chair, or the other way around, whatever I said first. Okay. Now, when I incorporate x3 and x4 in the objective function also, then x3 and x4 actually are not earning any profit for me. They are there just because of the slackness in the resource. Otherwise, since they do not exist physically, so they do not correspond to some quantity that can be sold in the market and give me some revenue. Okay. So what we do is we associate a zero profit for them. Okay. So that means their contribution in the objective function is zero. Right? No matter whatever positive value they take, even if they take a positive value, they are not going to contribute towards my profit function, because their contribution is zero. Okay, so we introduce slack variables in the constraints and in the objective functions, right? But at a level zero, with zero coefficients, and we assume that these slack variables are also non-negative. Okay. But say supposing you have some variable which is more than or equal to type. Like supposing this variable was 5x1 plus 4x2 more than or equal to 120. No matter, less than na hota, more than hota. Okay. So basically what is happening is that your utilization or whatever it was is more than what is available. Okay. So basically what is happening is that there is a surplus utilization. Okay, because my left hand side is more than equal to my right hand side. So to make them equal, what should be done? They should, some variable should be subtracted from the left hand side. So in that case, when we introduce a variable, I would have written plus 4x2 minus x4 or x3, whatever it was, equal to 120, because my left hand side was greater. Okay, and because it was greater, there was a surplus thing going on here. So that's why these variables are called as surplus variables. And of course, they are still non-negative. They cannot be negative. They can be at the most zero, but they have to be positive. Okay, so basically, depending upon the sign of the constraint, we introduce the slack or the surplus variables to convert inequalities into equalities. Is this clear? Hmm?